Okay, so like I say, we want to basically come up with the conditions for this sub-object I to just consist of the isolated vertices of A. And as I say, we want three conditions. The first one is that I is contained in theta, which basically means I only has isolated vertices. The second one, well, let's deal with the third one actually first, which is that I union negation of I is the identity subobject, it's a full subobject. When the negation of I is the subobject classified by not chi I. So this one here, this implies that there are no edges in A connecting vertices of I. We know that I is just vertices because of this condition. But like I say, this says there's no edges connecting vertices of I. Why is that? Well, suppose there is such an edge, like in this case here. So I is these three vertices circled, let's say. Well, if there's an edge between them in the actual graph, like here, say, then it's going to go wrong because this edge is clearly not present in this subobject I. But see what happens when we do not on this is that this edge here is one of these absent edges. So when we do not, it becomes one of these absent edges over here. So this edge will also be absent in the negation of I as well. Okay, so what I'm basically saying is that this kind of thing here is going to be absent in I and also absent in the negation of I. So there's no way that doing I in union with I complement is going to have all the edges because that edge isn't there in either of them. Okay, so that's why this condition implies that there can be no such edges connecting vertices of I, sort of internal edges. And then this condition here, that I intersected with its negation, is empty. So consider this kind of edge. Well, in fact, maybe this condition's all we need, because again, if we take the negation of I, that's not going to have these edges which go from I to from inside I to outside I. It's not going to have those either. So this is probably all we need. But this one extra condition won't hurt. But anyway, we have these conditions basically, which are the conditions for I to be a subobject of A, only consisting of isolated vertices. And we can use these three conditions an alternative way, which is probably cleaner. And whether this can be formalized in a language of partial arrow classifiers, I'm not sure, but basically the cleaner way to say it is that I is the pullback of the second injection from hom v, blank to I should call it I2 of hom v from hom v, blank to 1 plus hom v, blank. It's the pullback of that along some arrow f from A to 1 plus hom v, blank. So it's basically saying it's a load of stuff that can get sent to a vertex. Either way, we have these conditions on I, which basically mean that I is a subobject of purely isolated vertices, and if we take the union of all such I, we get what I call ice A, which is the subobject of A consisting only of these isolated vertices. Yeah, say it more cleanly here. An alternative way to describe ice A is as a maximal subobject of A that is the pullback of this subobject I2 of 1 plus hom v, blank along some arrow f from A to 1 plus hom v, blank. Or we could describe it as the union of all of these. We could describe, we can describe it like this. It's the union of the pullback of I2 along G for every arrow G from A to 1 plus hom v, blank. So what are we going to do with this? Well, basically, we can use this ice A to get us the set of isolated vertices, and we can subtract them from the structure. So now let's solve this problem that we're interested in. So if we have this arrow eta, is it eta? No, this isn't. Yeah, I think it is. It's eta. From hom E to the subobject classifier that just highlights this arrow pointing out of the present vertex. Let's say we have some graph X, and we have some subobject S of it that we're looking to find the kind of out neighborhood of. So maybe S is just like a single vertex of X or whatever. So we're now solving our problem. So what I'm saying is that if we pull back eta over chi of S, that's going to give us the subgraph of X, which has all the vertices of X present. because wherever chi s would send a vertex, it will belong to this sub-object eta of omega. So when we pull back along chi, that vertex will be present. So all the vertices will be present in X, but the only edges that will be present in X are the edges which are going from stuff that's inside the sub-object S to stuff that's outside the sub-object S. So this half solves our problem, but then what we need to do is get the isolated vertices. So if we let B be the sub-object of X, which is the pullback of eta along chi of S, then if we take the full sub-object of B in intersection with the negation of ice B, that'll be basically like this neighborhood graph, but only the non-isolated vertices of it, and that's what we want.